Hello again. Today we're going to look at some more derivative rules and do a couple more examples. So here we have the derivative rule for exponents, specifically e to the x, which is a very simple derivative rule. The derivative of e to the x is simply e to the x. Now, e is a special base. E is a number, it's approximately 2.718. It is a irrational number like pi. It keeps on going forever, seemingly without a pattern to it. But it is a special base, especially for calculus, because it's the only base whose exponent, the derivative is just itself. Any other base gives you a much more complicated derivative equation. If you had a different base, like let's say base 2, so you're taking the derivative of 2 to the x, the derivative would not simply be 2 to the x. It would be 2 to the x times the natural log of 2. Remember, natural log is log base e of 2. Okay? And if you had any other base b, the general formula is b to the x times the natural log of b. As you see, a much more complicated equation than e to the x. So you're going to see e to the x all over the place when it comes to derivatives, because it's actually the base that makes the derivatives the simplest. Rather than any other base, the equation is going to be more complicated. So just get used to seeing e to the x all over the place. It really is the exponent that has the simplest derivative rule to it, and that's why they use it so often. Okay. Let me also write down the derivative rule for ln of x, which is log base e of x. And that rule is simply 1 over x. And once again, log base e of x is the base that has the simplest derivative rule when it comes to logarithms. If you had log base b, then it would be 1 over x, and then you divide by an extra ln of b. So the way I like to think of it, to remember it, is the derivative of b to the x is b to the x times ln b, whereas the derivative log base b of x is 1 over x divided by ln of b. So one rule you multiply by ln of b, the other rule you divide by ln of b. Anyway, that's just the way I like to keep them straight. But these are the bases that you're going to see most often, base e for e to the x and ln of x. Anyway, then we come to the derivative of the 6 trig functions. Okay, you are going to have to just sit down and memorize these, although there are certain patterns that you can use to help you memorize them. I like to memorize these in blocks of 2, like sine and cosine go together. Their derivatives only involve sine and cosine. The derivative of cosine, the derivative of sine is cosine, and the derivative of cosine is negative sine. Then tangents and secants is a second block of 2, whose derivatives only involve tangents and secants. So the derivative of tangent is secant squared, the derivative of secant is secant x tangent x. And then the last group, cotangents and cosecants, their derivatives only involve cosecants and cotangents, just like tangents and secants. In fact, there's a very similar pattern to it. The derivative of tangent is secant squared, whereas the derivative of cotangent is negative cosecant squared. It's still the other thing in their block squared. Whereas secant and cosecant have similarities. The derivative of cosecant is, derivative of secant is secant x tangent x. That's the product of the two things in its block. Whereas the derivative of cosecant is negative cosecant cotangents. It's the negative product of the two things in its block. Finally, one other thing that you might notice is half of the derivatives are positive and half of them are negative. Well, the 3 that are negative are cosine, cotangent, and cosecant. And those are the 3 trig functions that start with the letter C. So the 3 trig functions starting with letter C all have negative derivatives. Anyway, those are just a couple of little patterns to help you remember them, but you are just going to have to sit down and memorize them all. Okay, now let's do some examples. of some derivatives that use exponents or trig functions. Okay, so let's do x squared e to the x is our function. Our goal is simply to find the derivative. Okay, this is a product, so we're using the product rule. That's the derivative of the first times the second plus the first times the derivative of the second. So I wrote out the pattern. Okay, now the derivative of the first would mean the derivative of x squared, so that's 2x, times the second, so that's e to the x, plus the first, which is x squared, times the derivative of the second. The derivative of e to the x is simply e to the x. So that gives you 2x e to the x plus x squared e to the x. However, you can factor that. You can factor out an e to the x out of both of those, leaving 2x plus x squared times parentheses e to the x. Okay. You could also do some further factoring x out and writing it as x times 2 plus x. But anyway, this is probably how most people would simplify it and leave it. So that's a pretty simple one to start with. Let's look at one that's a little bit more complex. F of x is going to be x squared plus x divided by e to the x. Okay, so this one's a quotient, so it's going to involve the quotient rule. Okay, so let me just write out the pattern for the quotient rule. It's the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. So that's the general pattern. Okay, so the derivative of the top is 2x plus 1. The bottom is simply e to the x minus the top, so x squared plus x. And then the derivative of the bottom, well, the derivative of e to the x is just e to the x. And then the bottom is e to the x squared. If you prefer, you can write that as e to the 2x. You know, the powers raised in succession multiply together. Okay. Notice that you can factor out an e to the x out of everything. And while I'm at it, I'm going to distribute that minus to make this minus x squared minus x. And there I factored the x squared out of everything. I'm just going to leave the bottom as e to the x squared rather than writing it as e to the 2x, because it makes it clear that one of the e to the x's you can cancel. So this e to the x goes away, and this power is reduced down to just e to the x to the first. Now simplifying the numerator, we get negative x squared plus x plus 1 all over a single e to the x. So that's our derivative. So notice that you need to remember, like, your exponent rules and canceling in order to simplify equations. Because a lot of times the teacher doesn't like it, left in a more ugly, complicated form. Try to simplify it as much as possible. Okay, next let's do a problem that involves some trig functions. Okay, so let's say that f of x is equal to 3 times the cotangent of x plus 4 divided by the cosecant of x. And our goal is to take the derivative of this. Okay, there are two ways to do this problem: the hard way and the easier way. So I'll outline the hard way first, but then I'll show you how to do it easier. The hard way would be to leave this equation as it is and just take its derivative using the quotient rule. The derivative of cotangent and cosecant are a little bit messy, and you're going to get a big, long fraction, and then you'd have to simplify it. Well, as it turns out, a much better approach is to simplify this using just some trig identities first before you ever take the derivative. You can actually simplify this equation a lot, and then it makes taking the derivative so much simpler. So cotangent is cosine over sine, and cosecant is 1 over sine. So that's just by the definition of cotangent and cosecant. Next, I want to get rid of the little fractions. They both have the same denominator as sine of x. So simply multiplying by sine of x on the top and bottom should get rid of all those little fractions. Okay? So then distributing sine x times 3 cosine x divided by sine of x, the sine of x is canceled, leaving 3 cosine of x. And then 4 times sine of x. The denominator is simply sine divided by sine, which is 1. So when your denominator is 1, you can just get rid of it. So the equation simplifies to be 3 cosine x plus 4 sine x. See, and that's going to be a lot simpler to take the derivative of because we don't have to use the quotient rule anymore. Okay, so that was just simplifying the original function. Now applying the derivative rules. The derivative of cosine is negative sine, so this becomes negative 3 sine x, and the derivative of sine is positive cosine, so plus 4 cosine x, and that is your derivative. So the thing to take away from this problem is, if you see a way to simplify your function before applying the derivative rules, do that. Because then you'll have a simpler function to take the derivative. It won't get way complicated, and then you'll have to end up trying to simplify something that is much more complicated, to simplify than if you had just simplified the original problem to begin with. So if you ever see a way to simplify the original equation, do that, because it's usually the best way to go. Okay, I think I have one more problem, and it's going to be a little bit more advanced than these. Okay, let's say that we have a function and we want to find the x-intercept of the tangent line to the graph f of x equals x squared plus x times cosine of x plus 4 at x equals 0. Okay, so before we can find the x-intercept of the tangent line, we have to find the tangent line. In order to get the equation of a line, we need to know a point on the line and the slope of the line, point and slope, and then we can plug into our point-slope equation. Well, to get the point, we have x equals 0, that's the x-coordinate of the point. We can just simply plug in 0 to get the y-coordinate. Let's just get that out of the way. So if we plug in 0 for x, we get 0. 0 times 1 is 0, plus 4. So f of 0 is 4, and therefore our tangent line passes through the point 0, 4. Now we need the slope of the tangent line, which is the derivative. So now we need to take the derivative of this equation. So the derivative is 2x plus, and then this is a little product rule. So the derivative of the first is 1 times the second cosine of x, and then plus the first x times the derivative of cosine, which is negative sine of x, and then the derivative of 4 is 0, so that just goes away. Now we want to plug in 0, so the derivative at 0 is 0, cosine of 0 is 1, and that's 0 times 0, so that's just going to be 0, so we just get 1. And remember, the slope of the tangent line, the derivative is the slope of the tangent line. So our slope is 1, our coordinate point is 0, 4, and then plug that into the point slope equation of the line, y minus y1 equals m times x minus x1, where y1 and x1 were the 4 and the 0. So I already plugged that in. And now let's solve for y. Distributing that just gives you x, and then adding 4 to both sides, you get y equals x plus 4. That's the equation of the tangent line. So one last thing to do, they wanted the x-intercept of the tangent line. So now that we have the equation of the tangent line and we're trying to find the x-intercept, the x-intercept is where you cross the x-axis, and it's where y equals 0. If you're ever finding the x-intercept, you want to plug in 0 for y. If you're looking for the y-intercept, plug in 0 for x. So you just plug in 0 into the other variable. So x-intercept, plug in 0 for y. and then solve for x, and we get x equals -4. That is the x-intercept of the equation of the tangent line. Okay, so just want to do one problem that's a little bit more harder than just finding the derivative of the equation. Of course, we had to find the derivative in the middle. Anyway, so that's going to be it for today. Hope you have a good day.